One of the big trends in technology at the moment is vector databases, which are often used in conjunction with language models. In this video, we're going to look at how we can use PostgreSQL as a vector database by adding an extension called PGVector. We're going to see how to set that database up using a Docker image, and we're also going to dive into how to actually create these vectors or embeddings using Langchain and OpenAI, and then store those vectors into the PGVector database. And finally, we'll show how to query that database using both Langchain and also in raw SQL in order to pull out some insights based on the vectors that are stored in that database. So let's get started. I have the GitHub for PGVector open here. I'll leave a link to this below the video, and you can see the gist of what this is. It's an open source vector similarity search for Postgres. Now, there are other vector databases out there such as 𝗖𝗵𝗽𝗀 and 𝗵𝗽𝗀 and others, but the benefit of Postgres is that it comes with all of the normal benefits of using a database. As you can see here, it's got ACID compliance, point-in-time recovery, joins, and all sorts of other brilliant features. And Postgres is a mature database, it's reliable, and it's used a lot in the development community, so you can trust PostgreSQL, and this extension will allow you to turn it essentially into a vector database that allows you to query for similarity. Now, in this video, we're going to use this piece of text here. It's the State of the Union text, and I'm going to leave a link to this below the video. I've already downloaded this, and it's here in this local directory. Now, I've also got a Jupyter notebook open here, and we're going to use this notebook throughout the video. Now, what we're going to do in this notebook is we're going to use Langchain, as you can see here from the imports, and we're going to take that State of the Union text and we're going to split it into chunks, and then we're going to embed each chunk into a vector. And we'll walk through more about what that means as we go through the video. What we've imported here from Langchain is the text loader, and we can use that to load in text files. We also have the recursive character text splitter, and this is used to split up a piece of text into chunks. And finally, we have the OpenAI embeddings object imported from the Langchain.embeddings module. Now, embedding is the process of turning a piece of text into a vector, and the vector that's produced from that is also known as the embedding. We're going to see in this video how we can use the OpenAI embedding models, and Langchain can call these on your behalf. And from that, we'll get a set of vectors, and we're going to later on store them in PostgreSQL using this PGVector extension. Now, because we're going to be calling the OpenAI APIs, we also need a .env file here that contains an OpenAI API key. And we use the Python.env module here and call this load.env function in order to load that into your application. So that's a bit of setup here. Just make sure you download the State of the Union text or any other piece of text that you want. And what we're going to do now is read that text in using the text loader. And of course, in order to make this work, you also need to install Langchain.env and OpenAI in your environment. So I'm going to copy a command just above this cell here. I'm going to insert the cell above. This is the command that you would need to run. It's a pip install command, and the libraries are Langchain, the OpenAI library, and Python.env. So I'll comment that out, and what we're going to do is get started. We have, as I said, a file called stateoftheunion.txt here. I'm going to copy that and we're going to bring it into the notebook, and what we're going to do is we're going to create a loader object by instantiating the text loader that we've imported above. And let me create some cells here so that we can see this better. We pass the name of the file into this text loader, and we're also going to pass an encoding and set that equal to UTF-8. So that gives us a loader object, and we can get the documents from that by calling the loader.load function. So let's try this out. And in the cell below that, we're going to do a couple of print statements here. First of all, we're printing the documents. This is going to print each document that's loaded from that text loader, and that's only one document. As you can see in the second print statement, when we print the length of that list of documents, that gives us back 1. So now we have this State of the Union.txt loaded in using the text loader, and that's available as a document object, which is a Langchain native object. So now that we've got this document, we're going to split it into chunks, and we're going to use this object that we've imported from Langchain. It's called the RecursiveCharacterTextSplitter in order to do that. So let's go to the cell below here, and I'm going to create a variable called TextSplitter, and that is going to be an instance of this RecursiveCharacterTextSplitter. And we're going to pass two keyword arguments to this. The first one is the chunk size. That's the number of characters that we want to use in each chunk from the original text. In this case, we're going to say we want 1,000 characters in each chunk. And then when that has read 1,000 characters from the text, it's going to then create a new chunk after that. And when it creates the new chunk, we can optionally specify some overlap here. That's using the chunk overlap keyword argument. And let's set that equal to 80 in our case, just randomly setting that to 80 there. Once we've got the text splitter object, what we can do is get back a set of text by calling the TextSplitter.split documents function. And the split documents function, it takes in those documents that we loaded just above here using this text loader, and then when we called the loader.load function, that gave us back these documents which we're passing in as an argument to the split documents function, and that gives us back a set of chunks, essentially a set of texts that are 1,000 characters each, and that 1,000 characters is determined by this chunk size argument that we used on the text splitter. So let's now see an example of what these chunks look like. Let's print the very first one out to the notebook, and you can see we have some content here, and that's set to the first 1,000 characters of the very first chunk from that original text. And if we need to know how many chunks we have after splitting this up, we can print the length of the resulting texts, and you can see here that we have 42 chunks. So now what we have is we have a set of chunks, we have a set of texts that have been gathered from this original state of the union.txt file, and each chunk has 1,000 characters. What we want to do now is take each one of those chunks and create a vector or an embedding from the text that is contained within the chunk. And of course, a vector is just a set of numbers packed together into what is essentially like a Python list. So we're going to take each chunk here and we're going to create a vector from that, and we're going to do that by calling the OpenAI embedding models, and we pass to that some text, and then it will return to us a vector for that text, and later we'll store that vector in the PGVector database. Now what I'm going to do is go to this documentation on the OpenAI website, and this has some information about embeddings. And you can see it has many use cases embeddings, for example search, clustering, recommendations, anomaly detection, diversity measurement and classification. And as it says, an embedding is a vector of floating point numbers. And the key point here is that the distance between two vectors measures their relatedness. It's a similarity metric between the two pieces of text. The closer the distance, the more similar the texts are. And this is something that is used a lot with vector databases to find the appropriate pieces of text when you're calling the OpenAI or other language models. So how do we get these embeddings? Let's scroll down. We can get the embeddings by sending our text to the embeddings API endpoint, and we can also specify a choice of embedding model. And the default that is used by Langchain, and the one that we're going to use, is this one here, text embedding ADA, and it's version number 2. The response that we get from that will contain an embedding which we can then save to PGVector. So let's get started in doing this. We're going to go back to the notebook and scroll down. Let's create an embeddings object here by instantiating that OpenAI embeddings object that we imported at the top here, and that was from the Langchain.embeddings module. We imported that. Let's now instantiate it, and then we're going to test its usage by getting a vector back when we call the embeddings.embedQuery function. So this is a function defined on the instance of OpenAI embeddings. It's called embedQuery, and we can pass any string to this. For example, in this case, testing the embedding model, and that's going to give us back a vector, and it's going to do that by calling the OpenAI API, which will return this vector that you can see below. And remember, the vector is just like a Python list of floating point numbers, and these numbers are, according to the OpenAI embedding model, representing this text in the best possible way using these floating point numbers. And what happens with these OpenAI embedding models, they return the vector and it has a particular dimension. So let's look at that now. You can see the dimensionality of the vector. It has 1,536 numbers in that list, so it's 1,536 dimensions. So when you use this OpenAI embeddings object in Langchain, you are making queries to the OpenAI API, so you will need that API key to be set up. Now the goal here is we're going to take this vector and we're going to store it in PGVector in the Postgres database, but not for this particular piece of text. We're going to do it for the chunks that we've extracted from the state of the union text. So before we do that, let's see an example of how we can get an embedding for the first 5 chunks that we've extracted in that text. I'm going to create a variable here called docVectors. And again, we're going to use this embeddings object here, and this time we're going to call another function. It's the embed documents function. And we're going to use these texts that we extracted earlier on. So what I'm going to do is pass in a list comprehension here. And for each text T, I'm going to get the page content from that. And that's going to be for each T in these texts. And we're only going to use the first 5 so that we don't send a call to the OpenAI API for every single piece of text in this demonstration here. Once we've done that, we can print out the doc vectors below, and you can see I'm actually getting a module not found error here. So if we scroll to the bottom, it's saying we could not import the tick token Python package. So let's copy the pip install command here. Apparently we need this package to use the OpenAI embeddings. So what I'm going to do is paste that in here. Remember the exclamation mark at the start of that. If you're in a Jupyter notebook, that tells the notebook that we want to run this as a command. And once that's completed, I'm going to clear it out, and we're going to go back up here and we're going to rerun this cell. And hopefully this time we're going to get back 5 vectors for each chunk that we've sent to the OpenAI embedding model. Now remember, there's a lot of numbers in these vectors, so we're not going to see that particularly clearly. What I'm going to do is print out the length of the vectors. We should see 5 vectors coming back here. And let's do this in a new cell so that we don't always call that API. We can also print the very first document vector by indexing in at 0 here, and we get back the first vector for that particular chunk, the very first chunk of the State of the Union text. So at this point, let's introduce PGVector into the equation, and we're going to see how we can take the vectors that we are getting back from the API and store them in a PostgreSQL database, and then query that database to find vectors or texts that are similar to a given query. Now before we do this, let's ask the question, why might you want to use a vector database? Well, one reason, as you can see here, is that when you send a query to the OpenAI embedding API endpoint, each request that you send is going to incur some sort of cost, and if you're sending lots of them over the same pieces of text, that is going to be inefficient. It's going to cost you money that you could save by taking the resulting vectors and storing them in a database. So if you have a lot of documents in a corpus and you split these documents further into different chunks and you send all of those chunks to the OpenAI endpoints, if you continually do that for the same chunks in your applications rather than storing them in a database, that is inefficient. It's going to cost you money that you wouldn't need to spend otherwise. And of course, storing these vectors in a database is also faster. Rather than going over the network and getting the embeddings, you can query the database, and that can in many ways be faster as well. And one final reason, vector databases, they come with built-in similarity functions such as the cosine distance as well as the L2 norm or the L2 distance. These distance metrics are built in, and that can help you if you're finding similar pieces of text to a given query. So let's get started, and what we're going to do is we're going to go to this Docker image, and this is an image for the PGVector extension for Postgres, and you can copy this docker pull command here and we can paste that into the terminal, and this is going to pull the PGVector image from Docker Hub, and it's going to store that locally for you to use. Now in order to do this, if you're on Windows or a Mac, you will need Docker Desktop installed. Once we have that installed, we can run another Docker command. It's the Docker Images command. This is going to show us all of the images that we have on our computer. And you can see at the top here, the PGVector image is now here. So the question is, how do we take this image and create a container and run that container based on the image? Let's go back to the PGVector GitHub page. And as you can see, it's got additional installation methods. This is the one with Docker, and it's got that Docker pull command that we just ran. And below that, as it says, it adds PGVector to the Postgres image, and we are going to run this particular image the same way as we would run the Postgres image. So let's click that link, and we're going to be taken to the Docker Hub page for PostgreSQL. And in order to start the Postgres image, I'm going to scroll down to this section here, and we have a Docker run command here that tells us how we can run the Postgres image and start a container based on that image. And one thing we need to do here is specify the Postgres password when we use that Docker run command. So we're going to use a very similar command to this one. I'm going to go back to the terminal and I'm going to clear out the Docker images here, and we're going to use the Docker run command, and we're going to give the resulting container a name of PGVector-demo. We're then going to set an environment variable within the container. We can do that using the -e flag, and we're going to set the Postgres password here, and in my case I'm going to set that equal to test. We're also going to add a port mapping here from port 5432 on the host to 5432 within the container, and that's going to allow us to connect to that port in the container from our host. And finally, we need the name of the image that we want to start a container from. If I scroll back up here, it's this PGVector image that we downloaded, so we can paste that in at the end of the Docker run command. So let's try this out just now. If we run this command, you can see that things are starting up here, and at the bottom it says that the database system is ready to accept connections. So we are started, we are running, and now we can use PGVector within our Postgres database. So let's now see how to do that. Now I'm going to use pgadmin in order to connect to PostgreSQL and allow us to view the tables through a graphical user interface. So I've got PGAdmin open here, and on the browser on the left hand side I'm going to right click and I'm going to create a new server group here. And I'm just going to call this server group bugbytes. That'll add that to the browser on the left hand side, and then we can then register a server within that group. And I'm just going to call this server PGVector test, and then we can define the connection details on the connection tab here. Now the host is going to be localhost. We can access the PostgreSQL database that's running in the container through localhost because of that port mapping that we added. And the ports were port 5432, so we can keep that as it is. And we can use the password that we specified in the docker run command, and that was test. Once we've done that, we can hit save here, and hopefully this is going to make the connection, and it does. As you can see here, we now have access to this PGVector test database. If we look at the databases in that server, you can see we've got one called Postgres. For the demo that we're about to do, I'm going to create a new database here, and I'm just going to call this vector_db, and then we can hit save, and that's going to create a new database on that server called vector_db. What we're now going to do is make a connection to this database on our Jupyter notebook, and we're then going to store the vector embeddings that we got back from the OpenAI embedding models into this database. So let's see how to do that now. If we go back to the browser and go back to our Jupyter notebook, we're going to need to install a couple of libraries here. Now in order to make the connection from Python to Postgres, we need the Python driver for PostgreSQL, so that's this here, it's the 𝗖𝗵𝗽𝗀𝗲𝗲 binary. And we're also going to install another library called PGVector, and we can use the pip install command to get both of these into the notebook environment. Once these are installed, we're going to go to the documentation for Langchain, and there is a page here on the PGVector vector store, and this is one of the many vector store integrations that Langchain has. You can see others on this left hand sidebar. For example, we have integrations with Azure Cognitive Search, Cassandra, Chroma, and many more here, including MongoDB Atlas as well. Now we're going to follow some of the documentation on this page here in order to use the PGVector object in Langchain. So let's get the import into our notebook from langchain.vectorstores.pgvector. We're going to go back to the notebook, and I'm going to remove the pip install command, and we're going to import the PGVector object. Once we've got that, we're going to then set up a connection string to our PostgreSQL database, and this uses the Postgres protocol here, and then we have a user of Postgres who has a password of test, and remember we set that in the docker run command. And then we have this @ symbol, and we have the host here, which is just localhost with port 4532. Finally, we have a slash, and then we have the name of the database that we're connecting to. In this case, it's the vector_db, and if we go back to PGAdmin, that's the name that we gave this database here. What we're also going to do is go back to the notebook, and I'm going to set up a variable here called collection name, and we're setting that to state of the union vectors. What we're now going to do is instantiate this PGVector object, so let's copy that, and we'll store the instance in a variable called db here. And we're going to pass some parameters to the PGVector object. We need to pass the embedding model that we're going to use here, so we can use the embedding keyword argument, and we're going to pass the embeddings object that we created above. So if we go up here, we created this here when we instantiated the OpenAI embeddings object, and that's the object that's used to call the OpenAI embedding API endpoint behind the scenes. Once we've got that, we can also pass our documents into this PGVector object. These are the documents that we want to create embeddings from, and we're going to use the texts that we chunked up here from the text splitter. So let's copy that and paste it into this argument. We also want to specify a collection name here, and we're going to set that equal to the state of the union vectors. And finally, in order to actually make the connection to PostgreSQL, we need to also pass a connection string here, and we're going to do that using this string that we built up just above here. Now before we run this, there is a small mistake here. Rather than instantiating PGVector directly, we are going to call a function on this, and that's the fromDocuments function. And this is kind of like a factory function. What this does is it takes in the documents and it creates the embeddings from those documents and stores them in the database. So we're using the PGVector class, and we're calling the fromDocuments static method here in order to create this db object. So let's now try to run this, and we're going to see that this gives us back an error. And if we go to the bottom here, the error that we're getting is that the type vector does not exist. Now this is a type that's added to Postgres by the PGVector extension. So this implies that PGVector is not set up on this vector DB that we have here. So how do we enable the PGVector extension? It's already loaded into the Docker image or the Docker container. What we need to do is enable it on this database. We can do that by using the query tool on pgadmin, or you can use the psql command line tool. All we need to run here is the create extension command, and we can pass the name of the extension. In our case it's vector, and when we run this we get back the create extension query returned successfully. And now if we go back to our notebook here and rerun this, hopefully we are not going to get that error anymore, and indeed that has completed successfully. So we've called the PGVector from documents function, we've passed the embedding object that we want to use to create the embeddings, as well as the text that we want to embed. So the question is, has this added anything to our database? Let's go back to pgadmin, and we're going to go to the schemas here, and we're going to go down to the tables within this schema. And you can see we now have two tables here. We have a Langchain PG collection table. Let's have a look at all of the rows in that table. This gives us back a single row, and it contains a UUID along with a name, and that name is matching the collection name that we set in the Jupyter notebook, state of the union vectors. And we also have another table here of Langchain PG embedding. So let's look at the first 100 rows of that table, and we're going to see what has been created here when we called that from documents function. I'm going to make this bigger here, and we can see we have a UUID, we have a collection ID, and that matches the state of the union collection that we set. But the important column here is the embedding. This is storing the embedding that we got back from the OpenAI API. It's storing it in this column, and it has a type of vector. This is a type that's added by the PGVector extension. And if we scroll to the other columns in this table, we also have a document column. This stores the text from the chunk that was used to create the vector. So importantly, this table contains the embedding and the original document for that embedding. And Langchain has stored all this into PostgreSQL when we called that from documents function. So how can we actually use these embeddings that have been stored? Let's see an example now. If we go back to our notebook, I'm going to go down here to the cell below, and I'm going to define a query here. Let's say, what did the president say about Russia? We can then use this DB object, and we're going to call a function on that called 𝗖𝗵𝗽𝗀𝗲𝗲. So I'm going to tab over here for some auto completion. It's this function here, 𝗖𝗵𝗽𝗀𝗲, and we can pass our query into that. And as well as the query, we can pass the number of documents that we want to get back. Let's say we want to get back 2 vectors or 2 documents from that table that are most similar to the query that we've issued above here. Let's store the result of that in a variable called similar, and we can loop over each of these and print them to our notebook. So for each document in that similar return statement, let's print them to the notebook. And if we look below at the documents that are coming back, you can see that the content does explicitly mention Russia in these comments, and that is true for the second document as well, which is talking about Putin and Russia. So what's happened here is we've taken this query, what did the president say about Russia, and we've called the similarity search with score function, which under the hood is sending a query to our PostgreSQL table, and that query takes the text that we're passing in here, and it is automatically embedding that using the embedding model that we have here in the from documents function. And what's being returned are the 2 most similar documents to this particular query, and this is very useful in our applications. If we have a large corpus of embedded texts, we can very quickly find the texts that are most similar using the similarity metrics that are built into PGVector and other vector databases. And each document that is returned here not only contains the document object with the text, but it also contains this distance metric here. And the lower the distance, the more similar the text is to the original query. And you can see the distance here has a value of 0.56, the one below that of 0.57. So these are the 2 pieces of text that are most similar to the query that we passed in. And the PGVector extension allows us to find these using that geometric distance calculation that it adds to PostgreSQL. Now if we go back to the GitHub page for PGVector, we're going to look at the section here, and you can see that create extension command that we had to issue earlier on. What we also have is the ability to insert embeddings into a table using the normal SQL insert into statement. And you can see we can also create tables and use the vector data type on a particular column. If we scroll down, what I'm going to look at is some of the new operators that are added to the database by PGVector. We can get these here, for example, in the distances section. We have this operator here. We also have this one here for the negative inner product, and we have the cosine distance operator here. So we can use these different distance metrics, and the top one I should have said is the L2 distance. We can use these to take a vector and find the most similar vectors based on the distance in the geometric vector space. So let's see an example of how to issue a raw SQL query and find this information. What I'm going to do is go back to the Jupyter notebook, and we're going to get an embedding for a random query, or rather we can actually use this query that we had above. So I'm going to remove this code here, and I'm going to issue another statement here. We're going to use the embeddings object, and we're going to call the embed query function and pass that query into that. That's going to give us back a vector, and what I'm going to do is copy this vector, and we're going to bring that into an SQL statement. So to replicate what Langchain did, what I'm going to do is go back here and to the PG embedding table, I'm going to go to the query tool, and we're going to select a particular column from this table, the document column, and we're also going to add another statement here for the embedding in a second. The table we're getting this data from is the Langchain PG embedding table, and we are going to limit the results to 2 results as we did in the Jupyter notebook. Now what we're going to pass in here is not the raw embedding itself. We're going to calculate the cosine distance between every single vector in this table and the vector that we pulled out here for this query. So let's go back to PGAdmin, and we're going to use the brackets here, and we're going to put a statement in here. We're going to look at the embedding column, and we're going to use the cosine distance. And at this point I'm going to pass in a string containing the vector that we got back here from OpenAI. And this is actually a little bit easier to do if you print it directly with the print function in Python. It will then, rather than one floating point number per line, it will print it out like this. You can then copy that, and we're going to go back to PGAdmin, and we're going to paste that vector into this cosine distance calculation here. And that's going to be as a string. Make sure you surround the vector with the string characters, and then we're going to alias the result for each row in the table. We're going to call the alias cosine distance, and then finally if we go back to the SQL statement here, we're going to order the results by the cosine distance. And remember, the smaller values of the distance indicate the most similar vectors. So if we want to get the most similar, we can just call order by, because it goes from smallest to largest by default, and we can get the 2 most similar by limiting the results to 2. So this is an SQL query that is going to use the cosine distance between every embedding and this particular vector that we're passing in. It's going to calculate the cosine distance, and it's going to return to us the 2 most similar documents from that table to the query that we're passing in. So let's execute that query, and you can see the result that we're getting back here. When we expand this text, you can see that this is indeed talking about Russia. So there is a measure of similarity to the query that we issued, and we got back a vector for that query, and that vector is passed directly into the SQL, and we're using, well, I've changed this now to the L2 distance, but we can also use the cosine distance here, and we get back a set of results. And we can look at the second document as well, and you can see this is also talking about Russia. So we're getting back similar queries, and this is how PGVector works. You can use these operators over a vector column type, and if you pass another vector in as a comparison vector, it's going to return to you the most similar vectors in the table. And remember, the reason these are the most similar is because we are ordering by the cosine distances that we're getting back here. If you remove the ordering, it's just going to give you back, for each row in the table, the cosine distance as an additional column. And just to finish this video, I'm going to show one more query. Let's say we wanted to get the average vector in this table. We can use the average function in SQL, and we can pass in that embedding column, which remember is a set of 1536 dimensional vectors. We can get that average, and we're going to take that from the Langchain PG embedding table. So for every single vector in the table, this is going to return to us another vector of the same dimension that is the average of every single vector in that table. And this average vector can be thought of as representing the average piece of text in the corpus that we've passed into this table. And the average vector, you might also hear it called a centroid. So that's all for this video. In this video we have looked at the PGVector extension for PostgreSQL and how that can be used to store vectors using the vector data type, and how it also adds different operators that allow you to find the most similar vectors to another one that you're passing in as a query. We've also looked in this video at how to use Langchain tools such as the PGVector class in order to work with embeddings and integrate with embedding databases or vector databases. We've seen how to use this OpenAI embeddings object in order to call the OpenAI APIs for the embedding models and get back vectors for a piece of text, and then we store that text in the vector database, which can then be used later on in our applications. So I hope this video has been helpful. If you're interested in more videos on this type of content, just let me know in the comments. Thanks again for watching, give it a like and subscribe to the channel if you've enjoyed, and we'll see you in the next video.